Welcome to the second part of this small lecture series on modeling biological membranes. In this video, I will first give an introduction to the theory of varifolds with curvature. Then I will show how this setting allows us to prove existence of minimizers for the multi-phase Canham-Helfrich problem. I will then conclude with some references and perspectives. Varifolds are a concept of geometric measure theory that generalize immersed submanifolds of Euclidean space or of other manifolds. They were introduced in the 1960s by Young and Almgren with the very aim to tackle geometric variational problems with the direct method of the calculus of variations. This also explains their name, which is a concatenation of variational manifolds. A varifold of dimension m in an open subset omega of Rn is a non-negative Radon measure on omega times the Grassmannian Gmn of m-dimensional linear subspaces of Rn. So a varifold not just measures where the surface is located in space, but also which tangent direction it has. The elements of the Grassmannian can be represented by the projection matrices P on the linear subspace. The mass of a varifold is simply the induced Radon measure on omega. And thanks to the Ries theorem, by which Radon measures are in the duality to continuous functions with compact support, one can characterize varifolds by their actions on such test functions phi. Finally, varifold convergence is the weak star convergence of measures, which explains their favorable compactness properties. Yet, varifolds, being just Radon measures, can be very irregular. However, there is a type of varifolds that has more similarity to classical surfaces. These are the integral varifolds, abbreviated as IVM, which are equivalence classes of Hausdorff measures restricted to countably M-rectifiable sets M, and weighted by an integer-valued multiplicity theta, and such that the Grassmannian component of the varifold is located at the approximate tangent space to M, by this direct measure here. The action of an integral varifold on a test function then has this form here, and its mass is simply given by the area of M, but weighted by the multiplicity theta. And this property is indeed very reasonable. If two surfaces approach each other to eventually partly overlap, then their varifold limit will be given by the limit surface, but with multiplicity 2 in the overlap region. Here, a set is countably M-rectifiable if it has finite m-dimensional Hausdorff measure, and up to a set of Hausdorff measure 0 coincides with a countable union of C1 submanifolds. And approximate tangent spaces are then given by this blow-up limit here, and in fact, their existence is equivalent to countable rectifiability. Concerning the question of compactness of integral varifolds, it turns out that a bounded mass is not enough, as you can curl up a surface of fixed area to a point. The missing ingredient was identified by Allard, and it is the first variation. The first variation is given by the linear functional delta V, involving the surface divergence of a compactly supported C1 vector field U, which you can see here. And its total variation norm is given by this supremum here. If the latter is bounded, then the Radon-Nikodym theorem allows us to split the first variation in an absolutely continuous part and in a singular part with respect to the mass measure. That is, the density of the first contribution, the absolutely continuous part, is then the generalized mean curvature vector h bar of the varifold, whereas the singular part has the role of a boundary measure. Indeed, if V is an integral varifold supported on a smooth surface with boundary and the surface has multiplicity 1, then h bar and the boundary measure, they can be identified with the classical objects. And this identity here with the first variation is simply the divergence theorem for U on curved surfaces with boundary. So in total, compactness of integral varifolds requires bounds on mass and on the first variation, that is, on the mean curvature. Yet Allah's mean curvature vector is not enough in order to formulate geometric variational problems involving more components of the second fundamental form, as in particular is the case for the Canham-Helfrich energy. For this, one needs the concept of curvature varifolds. These were first introduced by Hutchinson, and then later Mantegazza extended the definition to include surfaces with boundary. So a varifold is called a curvature varifold with boundary if there exist curvature functions A and a vector valued radon measure, such that this integration by parts identity holds. And this again can be seen as a generalized surface divergence theorem, but now given as an integral over omega cross Grassmannian. And in the case of an integral varifold supported on a smooth hypersurface M, one recovers the classical extrinsic curvature variables by these formulas. So in particular, from A you recover the second fundamental form and so on. And let me note that on this slide, I've written all formulas using summation convention. That is, one has to sum over every index from 1 to the dimension if that index occurs twice. Still, the notion of curvature alone is not yet enough to formulate the Canham-Helfrich problem for varifolds. This is because of the spontaneous curvature, by which the Canham-Helfrich energy depends on the orientation of the surface as well. But luckily, the concept of a general varifold is easily extended to include orientation. One simply replaces the Grassmannian by the oriented Grassmannian, which you can see here, and its elements xi are simple M vectors given by this M-fold wedge product. And in 2D, the two vector xi is equal to U1 wedge U2 can be identified with the unit normal vector nu through the Hodge star map, which in this easy case just means that nu is the cross product of these tangent vectors U1 and U2. And one can map the oriented Grassmannian to its unoriented counterpart by the map Q. And the push forward of an oriented varifold V by Q will then be denoted by Q sharp V and is just an unoriented varifold as we know it. And one can further define oriented integral varifolds denoted by IVO, and they have then two multiplicity functions corresponding to the orientations plus of the tangent space or minus of the tangent space. And for the associated unoriented varifold Q sharp V, one simply has to add up these two multiplicities. Moreover, every oriented integral varifold also corresponds to an integral current denoted by TV, and in this case one takes the difference of the two multiplicities. So actually, currents are the geometric measure theory concept for oriented surfaces. So generally, an M current is an element of the dual space to the smooth, compactly supported M forms. And in particular, zero currents are just the ordinary distributions. The mass of a current is its duality norm, and the boundary of a current is just given by Stokes' theorem here. And the current is called integral if the current T and its boundary are both rectifiable. That is, their action on test forms omega is given by this formula, y theta is again an integer valued multiplicity. So let me conclude this crash course in geometric measure theory with the Federer-Fleming compactness result for integral currents with bounded mass and bounded boundary mass. So now we have all tools at hand to prove existence of multi-phase minimizers for the Canham-Helfrich model. And let me briefly recall the problem, which I've considered in a joint work with Luca Losardi and Ulisse Stefanelli. Our aim is to describe multi-phase vesicles with sharp phase interfaces like this. And this we do by minimizing the corresponding Canham-Helfrich energy, here written down for two phases. And the constraints are the closeness constraints, that is, the union of all phases must have empty boundary, and then we have overlap exclusively at the phase boundaries and fixed masses and enclosed volume. The first task is to formulate the Canham-Helfrich energy in this varifold setting. Since we are dealing with surfaces, we of course consider two varifolds in an open domain in R3, and we express the Canham-Helfrich integrand in terms of the curvature functions A and the unit normal vector nu. This shows that we need oriented curvature varifolds, that is, oriented varifolds or oriented integral varifolds whose non-oriented counterpart is a curvature varifold. Then the expression above leads to this definition of the generalized Canham-Helfrich energy as a functional on the oriented curvature 2 varifolds. And note that the curvature functions A are the ones of the unoriented varifold Q sharp V. For the generalized multi-phase energy, we then simply add up the individual Canham-Helfrich energies and represent the length of the phase interface by the total variation norm of the boundary measure, weighted by the line tension coefficient sigma. In fact, since we work with oriented curvature varifolds, there are two different notions of the boundary. First, the vector-valued radon measure for the Mantegazza curvature varifolds, and second, the boundary of the two current associated to the varifold, to the oriented varifold B. And the definition of the enclosed volume easily extends to oriented varifolds, where we just recall that the Hodge operator applied to the orientation psi is just the unit normal vector. We are now ready for our main result on the existence of multi-phase Canham-Helfrich minimizers. First, we fix some constants, such that in particular isoperimetry is respected, and further let K be a constant set in omega and denote d omega epsilon, a strip with 2 epsilon around the diagonal in the product space. Then, if the bending rigidities satisfy this inequality here, and admissible varifolds are such that they have compact support in K and bounded mass of the boundary of the current associated to the varifold, then the multiphase energy FCHN possesses a minimizer satisfying all the required constraints. So the proof is straightforward by the direct method. Under this parameter bounds here on beta and gamma, we get the convexity of the Canham-Helfrich integrand as a function of the curvature variables. And then one further can estimate the altunum of the curvature functions in terms of the energy and the mass. Next one employs the compactness results by Mantegazza for curvature varifolds and by Hutchinson for oriented varifolds to show convergence of a subsequence of a minimizing sequence VI of admissible varifolds. And here, let us note that we can estimate the total variation norm of the first variation in terms of the L2 norm of the curvature and the total variation norm of the boundary measure. Next, lower semi-continuity of the energy follows also thanks to convexity by Hutchinson's concept of measure function pairs. And finally, one can show that all constraints are closed. So let me briefly comment on how we guarantee that the individual phases VI overlap precisely at their boundary. Our condition estimates the scaling of the product mass of a strip around the diagonal in omega cross omega. And in case of two phases, the condition looks like this. And one sees that this rules out intersections with positive H2 measure, yet still allows intersections with finite H1 or H0 measure, that is, overlap at boundary lines or isolated points is allowed. So our minimizers have several properties. First, there is the question about the regularity, since we have just measures. And what one gets simply from the fact that we are dealing with curvature varifolds is that the phases VI are C2 rectifiable. That is, they are supported on a countable union of C2 surface inter free. And further, since the minimizers have finite Wilmer energy by this estimate here, we can bound their multiplicity theta by the Li-Yau inequality. Moreover, we can show diameter bounds of the supports of the minimizers by generalizing an argument due to Simon. And thus, our minimizers will not shrink to a point or expand to infinity. And in particular, the latter property allows us to remove the assumptions of support being fixed in a compact set we made for the admissible varifolds. So before I conclude, let me also give you a list of references. First for the Canham-Helfrich model for biomembranes, and second for varifolds. And to get more into these topics, I would recommend to have a look at both last references, that is the review by Seifert, and then also the lecture notes by Simon. So, what are the perspectives of this work and further questions? So in this video, I presented a proof for existence of multi-phase Canham-Helfrich minimizers in the case of sharp phase interfaces, but without any symmetry restrictions. But what if we have a continuous phase distribution rho? So together with Gaspar Jankowiak, Christian Schmeiser, and Ulisse Stefanelli, we have looked at this problem in the lower dimensional case of elastic curves with modulated stiffness, where we focused on the effect on the density-dependent bending rigidity beta. Another research direction is the study of the gradient flow, and together with Martin Kružík and Ulisse, we can show existence of generalizing minimizing movements in a suitable metric space of varifolds, but still for single-phase membranes. And the evolution of general multi-phase membranes still has to be addressed analytically. So that's it. Thanks for watching, and I'm waiting for your questions. Goodbye.